to introduce a very long time friend and colleague, Faisal Safi. Faisal did his PhD with me at the University of Waterloo many years ago.
More than a decade.
2005?
Five, yeah, I graduated
2005. Since then, he's been a world traveler. He's worked for companies in the US on CMOS image sensors. He's worked for McMaster University and Wilfrid Laurier University teaching at about the same time. Before going even further overseas to to Kuwait and the United Arab Emirates, and as I say, world travel.
Yes.
He's now back in Canada, working as a visiting researcher at the University of Waterloo again.
Yes.
And has agreed to come and give us a presentation on his most recent CMOS image sensor work. And thank you for coming on the Friday before the long weekend, and for supporting Faisal in his presentation. So I will have Faisal's presentation and then a chance for some questions and answers, and then we'll wrap up.
Thank you.
So thank you very much, and take it away.
Thank you indeed. Thanks so much, Richard. It's a pleasure to see you again. After such a long time, but we're in touch anyways. Thanks everybody for coming to this audience, to this seminar at the York University. So basically the title of my presentation, and that's actually summarize my work. So basically I work on extracting intelligence from biological systems and try to embed them in electronics. That's my research, and also in teaching, in education. That's the other side of my career. So
I think that's just the present, probably just the
or maybe a keyboard.
Yeah.
Okay. All right. So, all right. But to implement intelligence, we have to define it. We have to know what is it exactly. So it was really an aspect of the human being and was questioned since a long time. And I here basically get some codes, which are the milestones of my approach to this really exciting topic. So, for example, quoting Socrates from the Greek civilization, he said basically that a quote that is really famous. He says that I know that I'm intelligent because I know nothing. It sounds like something not funny, but it really reflects the very important aspects of intelligence, and that's the self-awareness, which is the hot topic right now of artificial intelligence, is to make the machine self-aware about themselves. And once that's achieved, things will really be totally different, and the AI will take off really exponentially. And it is taking off. So let alone to reach this stage. So this is a character of human being. The human being knows that he's intelligent because he can reflect on that. So self-awareness is really important. Now, forward a few centuries down by Albert Einstein, this quote says that the true sign of intelligence is actually not the knowledge, it's actually the imagination. That's the reflectance of the intelligence, and that shows the other aspect of intelligence, and that's the creativity. It will be creative. And how is that achieved? That's another story. But it's a reflection, one of the reflections of the intelligence. Again, in the current times, we can find lots of definitions of intelligence. Some of them that are really very important in business, in engineering and stuff like that, especially the emotional intelligence. That's very, very important. The linguistic intelligence, the analytic intelligence. So the intelligence in itself has multiple dimensions. So that's what I want to reflect in here. And this multidimensional aspect of intelligence is really something really mind-boggling. Why it reflects everywhere? That's another question we need to contemplate. And actually, even psychologists, they don't have one definition of intelligence as shown in here. So what is really intelligence from all these? These are quoting. There are other aspects of intelligence as well. So the bottom line is that there's no consensus of what really makes the intelligence. What is really intelligence? Okay. Okay. What's next? Oh, fine. Einstein, after 30 years working on the photons, and by the way, he got his Nobel Prize, not for his relativity, he got it for the photoelectric effect, basically describing the photon as, you know, in French, corpuscule. It's like an individual thing, you know, like a... He said that we don't know it's a photon, but yet we use it. We use it in the camera, we use it in PVs, we use it everywhere. But what is it? We don't know. Same thing for intelligence. We don't know the matter exactly, what is it and stuff like that. We see the reflections of this matter, and same thing for intelligence. In this case, let's harness it. Although we don't know it, it's not really a big deal. So for harnessing it, many approaches have been treated so far. The first one is the most well-known application, which is artificial neural networks. I started this research back more than 20 years in Malaysia, where I studied the artificial neural networks until recently, last year, I presented a paper on that. So this is based on the heuristic processing capability of the neural networks, okay? Which is part of the brain, basically. We are trying to mimic that intelligence of the brain. And that's been used and it's been used. There are many topologies of you know, neural networks and etc. So that's one of the applications of harnessing intelligence. Harnessing means biomimicry, okay? Now the second definition, or the second approach to harness intelligence is basically based on the brain. The faculties of the brain, they are really multiple. The brain can sense, can control, can process that the information of the sensing and as well as the control, and can do also something really amazing, extracting ideas or intelligence or knowledge, basically by looking at the environment and try to extract some knowledge out of the physical world. This is basically math origin if you think about it, okay? So the brain can do stuff, many stuff, not only one. And this integration of functionalities, that what dictates the intelligence, is the functionality integration too. To integrate many things in one single box, and that's what makes a phone, or the iPhone intelligent. I is for intelligent because it can do a lot of stuff, okay, in a single device. So this is, and by the way, back in the days when I was a student with Richard Hornsey, our group was called the Integrated Camera Group, right? And that's basically because we try to integrate functionalities on the camera. It's still going right now. Okay, now, I'm not gonna read everything. So the other aspect here, oh, okay, here before we move here. So basically the intelligence also is used to know how the world is doing. So this is not really application, it's just a thought, okay, about how really intelligence is made. The last application of intelligence is to extract information, and that's basically for security application. When we say we gather intelligence, we are actually extracting information from the data. So the extraction of information is also one of the applications of intelligence. Okay, having said that, back to, again, the Greek, to get some inspiration about intelligence. Who's this? So basically Aristotle said something really amazing. He said that nature does nothing uselessly. Everything has a purpose, everything has a use. And here another quote which I really admire by Kepler, okay, who is a great German mathematician and astronomer. He said the diversity of phenomena of nature is so great and the treasures hidden in the heavens so rich precisely in order that the human mind shall never be lacking in fresh nourishment. So still, there is tons of intelligence around us in the physical world as well as the biological world, okay? Alright, good. So where we go from here? So what we know and what we need. What we know is that intelligent design of biological systems have passed the test of the time. They have been here for millions of years and they survived. That means they can actually solve multifaceted problems of the life with that aspect of intelligence. Now, what we know also, or what we need is to also, as engineers, to face multifaceted problems as well, and we need intelligence to do that, okay? And one of them is imaging. Imaging is one of the engineering topics, and all engineering disciplines, they have these, constraints that are from different ways, from different aspects, and they need to be solved. And that, we need intelligence to do that. So this is a solution is provided by nature, in biology or elsewhere. And here we have problems in engineering that we can solve. And both of them, they share the aspect of tackling multiple problems at the same time. And why not get this for this and for that? Let's get biomimicry going with the imaging. Okay, and for that matter, I define or coined this name, artificially intelligent imaging, or AI square. AI square basically is like I square, which is the power formula for the heat that get dissipated from resistors. What we mean by that, so basically we're trying to get the power of the intelligence down to, or implement it into electronics. We'll go very quickly because some of the things that are deep and specialized in imaging, I will not really get you bothered with that, but I give you just a perspective of that. This is an overall picture of an imaging system. It starts by the scene, passed by the optics, get focused by microlens, filtered by the RGB filters to get the color of the image, and then converted that light into electrical signal, digitized, processed, and then enhanced, and bingo. So it's quite a pipeline of information from the optical domain to the digital domain. Okay, so this is basically the anatomy of a classical CMOS image sensor. Okay, all right, and things that are being done nowadays is that we implement more and more, you know, even figure recognition, things like that on the same chip. And that's what we call system on a chip. That's where really the intelligence of the image sensor is going right now, and the future is really without limit in this sense. So this is just basically a picture, a micrograph, a microelectronic graph of the picture. So basically, an image sensor consists of a sensing area, a control area, and a sampling area, and of course, you have the different, signals, input, IOs, basically analog and digital to get the image out of the chip. Just, an introduction about the application of our AI square formula. So, to implement the artificial intelligence, artificial intelligent imaging, we had approached it in 3 ways. 2 ways I approached in my PhD long ago, but lately I endeavored into the device level. So the system level, and for that we are going to try to biomimic the intelligence of biological vision at the system level. For that we have fabricated and successfully tested and published, of course, papers on pyramidal CMOS image sensor. The second one, AI square, but at the circuit level. When we say at system level, basically at the chip level of how to acquire the data. At the circuit level means we are digging down and trying to play at the circuit, at the pixel level in this case, but we will approach it in the spatial domain. And the last, which is the current research, is to approach it at the device level. All of these, they biomimic the the biological intelligence, biological visual system intelligence in one way or another. We will go really fast because the time will not allow to go in details, but here I give you the summary of that. So for the system level, so basically we try to acquire the image in the time domain. Basically what we do, we basically try to enhance the dynamic range, which is the ability to see basically bright and dark spots of the imager in a foveated manner. Now I will show you that in a second. So to design it, we approach it in this way. So basically we keep the active pixel sensor, basically the circuit of the pixel, which is the standard pixel and CMOS image sensor pixel, okay? While changing the architecture, basically the global architecture about how to sample. And for that we fabricated and made and designed this CMOS image sensor. We called it pyramidal, and you'll see in a second why we called it pyramidal image sensor. So quickly, again, so this is the classical image sensor array, okay? It's a matrix where we read row by row, okay? And as we read, we build the image and then we transfer it along. This is the raster scan, there is nothing new in that. So we took that and we make the one-dimensional row sampling, we twist it to make it a ring sampling, okay? And by doing that, we gain lots of things, of course, you will see later. This, because the image, the eye does not necessarily work like this. This was extracted from, or was used from the display technology, about the old TVs basically. But this is more into the two-dimensional way of sampling of the retina, okay? So here we take ring by ring, okay, the image, and then we read it out through these buses, the oblique buses, okay, surrounded by the sample and hold circuitry. Okay, good. So let's go very quickly into the details there. So this is basically the just a snapshot of that. So this is basically the image. This is the real chip. This is the pyramidal image sensor. So it's like you are looking at the pyramid from the top, and that's why we use that name. And basically these rings, you can see that they are surrounded by these 8 banks of sample and hold, because they receive obliquely the signal of the rings, which is now divided into 8 segments, and 8 segments that at the same time they send the output outside the chip, which makes the speed actually technically 8 times, okay, than the classical image sensor. So this is the thing, and that's it, and this is the pixel inside. Of course, it depends where you are in the ring, but more or less the shape is the same. Now photodiode, coming back to the raster scan. So basically what you do, you read row by row, and then you go back to the row, first row, and why you do that? To have same integration time for all the pixels, and the picture will look uniform, okay? Now, to add to that complexity of the pyramid, we put another raster scan, another change for the scan. Basically, we call it bounce. In that bouncing, so basically you read, this is just 1/8 of the image sensor. Basically, we go and read ring by ring, okay? And then as soon as we reach the edge, we go back bouncing to the first ring, and so far and so forth. In this case, we give each ring will have 2 integration times, and we'll have 2 images in this case. Let's see what's the outcome of that in the few. This is basically the mathematical extraction of that. I'm not gonna waste your time, and that's where I want to take you. Okay, good. So the blue here, or the purple, I don't know. This is the integration time for this image. And what does it mean? The integration time, this is one of the bouncing. This is the, I called it the outward bouncing, because I'm reading now bouncing from the inner ring and going out, okay? So this is the blue. And the red one is bouncing where? From the inner ring. So bouncing at the inner ring, at the outer ring, and then going inward. So as you can see, you get 2 images. So basically one, which is the blue here. So the integration time is so small here that it becomes almost dark there. So it's brighter at the periphery, as you can see. Have enough time to get some signal. And the opposite comes to this, which is, to the red, sorry. That, so it's brighter in the center because the integration time is large enough, okay? But it's shorter at the outer ring. Why? Because the integration time is small. By combining the 2, you get a uniform integration time there, and you get an image in here. But there's a catch in there. When you combine 2 images of multiple integration time, the dynamic range basically enhanced. And that's the nice thing about it. The dynamic range basically get enhanced, and the synthetic one, and it's an enhancement, so it's not optical dynamic range, because we made it. And actually, when you take a photo with your image at night vision, it asks you keep it still, and that's the reason is because it takes multiple exposures and build it, so it's artificial. And this is one of them, but this is at the ring level, it's not at the chip level. So the dynamic range enhancement look like this. This basically shows the ring order. This is the inner ring, and this is the outer ring. This is basically a 64 by 64 pixel, so we have 32 rings, okay? So as you can see, the dynamic range is very much higher in the inner ring, and decrease, and then increase. Of course, here it goes to 0 because the time did not change. The integration time was the same for both of them, and if you remember the intersection of the previous graphs, you found that at here, the integration time was the same for inner or outer ring. Okay, good! What can we do with that? This is just a 3D of that. We can play with the integration time and make that border to the end here. And guess what? You get what we call a foveated one. What do we mean by foveated one? We'll get to the fovea in a second, but it means something just that the dynamic range is enhanced much better in the core than the periphery. And why we do that? Because when we look straight, that's actually the highest resolution of the image acquisition of the biological system. That's the optical axe. And we'll get to that in a second when we talk about the biological vision. So now, the dynamic range enhancement is like that. So what is the dynamic range is like that? That's a good question. It gives us the opportunity basically to allocate the analog to digital converters more bits in here. If you convert the dynamic range into bits, you get higher bits in here. than there. So basically, what does it mean? I can allocate less resources to the periphery of less importance, okay, and keep higher, higher resolution for ADCs for the inner brains, okay? And that's the idea, because the biology does not give resources for vision all the same. No, it has this region of interest, ROIs, that only ROIs, they have the highest attention, highest resources in terms of processing and sampling, okay? We'll get to that in a second to see the proof of that. Okay, good. Now to see the, it's unfortunate is that the CMOS, we use here a CMOS 0.18 technology. At that time, it's not adapted for the imaging. Of course, to make it for imaging, it was by TSMC. If you make it for optimized, the quality will be much better. But in any case, I can show you, for example, here, when we take the inward scan and the outward scan, combine them, get half of that, we get a diffused image here, and this is the rolling scan in there. By comparing them, really, you get a nicer spot there, showing that it could resolve this bouncing scan much better at the center than the rolling scan, meaning that the dynamic range enhancement here is really valid. The same thing can be said for the second one, of course. The optimization was not there. But to add more to that, we found that something really interesting, which makes that architecture very interesting, is that for a standard image sensor, the distribution of the noise is basically mostly in columns. For reasons we don't want really to get into, because the audience is not for that specific area. And you can see when you do the Fourier transform of that, you find really high peaks here in the cardinal, in the x-axis. Now for the parameter imager, because the output bus is basically oblique, the noise is basically oblique as well, and the distribution now is not only in the horizontal axis but also in the oblique axis. So what? We know from biology that the human visual system, as well as most of the biological visual system, we have less perception of noise, or we have less perception of edges in the oblique here than the cardinals in the 0 and the 90. Basically, the cardinals, the axis here. So if you if you take, for example, I think it was Sharp or company, they took 500 of natural scenes and they made the Fourier transform of them average. They found this thing. Okay, you see the bandwidth of the noise, or the edges, is higher in the cardinals, the horizontal and the vertical, but is less in the oblique, making what? Making the pyramidal imager basically less perceptible for noise in here. So basically the pyramidal imager makes that noise less perceptible, and therefore it doesn't exist for human eye. Which is really nice thing about that aspect of noise distribution. The second one, the second approach of AI formula, is basically at the circuit level. And for that, we played with the time for integration time, now we play with space. Okay? So the sampling now of the image at the pixel level, now we try to play with that to do something. And that is, we don't treat all the region of the image the same importance. They are not all region of interest. Only those who we choose to be, we sum them at the highest resolution. And that's basically the philosophy of it. So how we do that? So basically we keep the standard sampling architecture, which is the raster scan, and we modify the structure of the APS to basically program the region of interest and choose which one we like. And for that, we designed a chip that we call multi-resolution CMOS image sensor. This one had issues at the technical level, and we did not pass all the final characterization, but I have to explain the idea just to show you how it's made. And basically, a few years back, I found a patent, I should have referenced it here, by Micron, and they took this from, they took the idea here and developed it further from one of the SPIE conferences, and the idea is the following. We have a matrix of the pixels like that, okay? Now, if we are interested on region, or region of interest, any region of interest, we keep it at the highest resolution, which is the resolution of the pixels. But the areas that we are not interested to get its highest resolution, what do? We brush it. We take the average of those pixels. And to do that, basically we create two averaging mechanisms by embedding in the circuit, we'll show you that in a second, by embedding in the pixel charge sharing circuitry, okay, to share the charge of the pixels both between the rows and between the columns, like painting. Painting, like this. You paint like that. So you get the what? You get the average. And that was the inspiration of doing that. We can see that circuitry in a second here. So that's, so again, we cannot really go in details because lack of time. Of course, we have a photodiode, we have a shutter transistor there, and we have these 4 transistors that play the game of doing the row averaging and the column averaging based on our program. We program the areas. And what we can get from this? Oh, we get a few stuff. This is simulation of Albert Einstein. Of course, I like this picture not because only I admire this guy, but because his mustache, the famous mustache, has highest resolution, right? I need his mustache. I like his mustache. So these are the different things that we can do with this architecture. So in this picture, we basically row average squarely everything around his face. You can see it's good, and that's why you don't have problem with that, because that's where your interest is to see his face. What do we bother with the periphery? So why we sample it at the highest resolution? And that's the idea. So this is one straightforward foveated image acquisition. Now the second one is random. We can basically randomly select which area we want at highest resolution and do average anything else. Of course, we can have not only one, we can have multiple fovea. So basically, where is that? Here, in this case. So here in this case, we took this fovea and we took his cravat at highest resolution. So we can multiple that. And actually in biology too, in one type of the hawks I read about, they have not only one fovea, they have 2. And when we read about it, it's basically because the hawk, he is trying to, chase a rabbit or any, prey. So they need to see their flight as well as their prey. Okay? So for that, the biology gave them, 2 fovea, the highest resolution, the prey and the safety. So, which is really something unbelievable that the biological vision is doing. And it's not only the only thing that we are going to face in biological vision, more. Now, also because we are able to program the kernels to lower the resolution, we can basically minimize the distortion, because basically if we do the averaging perpendicularly to the contrast, we can basically not touch the contrast information at all. In any case, this is just to say that we can basically enhance, we can compress the image without deteriorating the quality of it. Back to the biology. Ramon Cajal, long ago, he touched the retina here. He opened the retina and he tried to understand how we are acquiring the image. And he found basically across the optical axis in here, he tried to look at the distribution of photocells. First of all, in the retina here, we have 2 types of photocells, and they are here. We have the rods, which ones? The cones and the rods, okay? The rods, they are color, the cones, they are color dispersive. That they can't discern or can distinguish between colors, but the rods, they are color blinded. That's number 1. The connectivity between these photocells and the ganglions, which are the neurons that are responsible to take the electrical signal from these photocells, which use the electrochemical transducing to get the electrical signal to the visual cortex, they have different connections. The rods, they have one-to-one connections, and the rods, they have many-to-one connections. Okay, this is another aspect, and this basically takes us to the distribution. From here to distribution, the rods, okay, they have a very interesting distribution, and they basically are very low in density until we hit the optical axis, okay, and they go exponentially high. Why? Because the highest resolution. They are the best in resolving the color as well as the light information. The rods, on the contrary, they are higher on the periphery and they go down. For front side illumination, basically, as I said, basically we have the photodiode on the bottom, and on top of it we have all the the wiring and stuff like that. On top of that we have the color filtering and the micro lenses to enhance the fit factor and the sensitivity of the photodiode. This is the old technology, still used, but in low-end applications. Now, later on in the early 2010, the backside illumination technology comes, and basically the light is now basically should be actually on this side, okay? Because the light comes in here, or basically no, because the chips, they are flipped like this. So now the light, the wiring and the oxide between the layers of the front end CMOS, they are not really hiding the photodiode. So the light comes right to the photodiode, and that's why it's backside. So you use two chips, and the sensing chip where the photodiode is will take that light, okay? And from the bottom, basically, you can wire bond and things like that to make the ROIC readout IC for the image sensor. Now in the CMOS, it went also in a very interesting development, and that is from 2D to 3D. The classical FET, it's not shown here, I'll show it in the next slide. So it's used as a planar. It's a 2D technology, there's no question about it. This is the standard planar CMOS where we have the source and drain, okay? And we have basically the source and drain, and we have the gate. And it's actually 2D. Now, as you know, it's an old technology now with aggressive sub-micron technologies. Now the gate, the channel itself is a 3D. So no more 2D. Why 3D? Because again, the real state of the shrinking technology is getting really smaller and smaller and more expensive to waste to increase more functionality in it. Okay? So both CMOS technology as well as the CMOS imaging, they went from 2D to 3D. And if you think about the imaging technology, it's basically photodiode they are trying to basically integrate the light in the vertical direction rather than the horizontal direction. Why? Again, because we want to enhance the resolution. But by doing that, by shrinking the size of the pixel, what happens? This is basically the standard APS, active pixel sensor. These are the by increasing the resolution count, increase the number of pixels, stuff like that. By increasing that, what we are doing, we have to decrease the pixel size. And by decreasing the pixel size, we compromise the image quality. Why? Because if you think about a pixel, it's basically like a bucket for the photons, okay, where you do the photoelectric effect. As the bucket decreases and shrinks, the amount of rain or water inside that bucket decreases. So basically, you compromise the image quality. The biology does not do this because the biological vision does do things different way. So the idea now is to decouple really the resolution count requirements from the pixel size. And this is what the biology has done long ago, okay? But how can we do that in our technology? So right now what we do, okay, because the photocells, as you can see, they see the light, they sense the light on the direction of the light. They don't sense it in the planar. They sense it exactly along the path of the light. And they can actually sense even a single photons, okay? Which is really amazing, okay? So what can we do? Let's put the photodiode like that shape and make it like this. We get basically an N-type or P-type, whatever it is, and the other semiconductor around, and make a pillar. And that's an idea I started to actually think about it at the end of my PhD, but never had the chance to basically realize it until I traveled around the world looking for money and opportunities to do that. So when I touched the semi-empirical equations of the sensitivity of the pixel, again, this is referenced in a paper, I can show you that. I found that the sensitivity of this type of photodiodes is very interesting. It's actually proportional to the height of that pillar. And while writing that paper and finished, I found amazingly that poop frogs and some kind of fish called the Haplochromais bordoni, I don't know, it's maybe Italian fish, I don't know. What they have, very interestingly, that the photocells, they actually elongate when they have the light low, and they contract when they have the light high. That basically the biological visual system, they actually contract, they control the light, the height of the photocells to basically play on the sensitivity. When they have enough light, they contract. When they don't have less, they elongate. And of course, this cannot be for any value of h. Of course, it has a validation range. And that's what we are doing right now on fabrication as well as simulation. So this shows the proof that yes, the silicon can do the same like the biological photocells. And that's where the biomimicry is. We can build photodiodes that can have its sensitivity proportional to the height, which is something really interesting. And one more thing, the photodiode has the smallest footprint that we can do. The smallest in terms of technology. We cannot go beyond our limits. But then the only gain we can control is the height, which is more or less unlimited. Now, because we are dealing with photodiodes, and photodiodes, they are not only for sensing, they are also for converting the energy of the light into power. That, using basically the responsivity equation and sensitivity of photodiode, we proved also in a recent paper that the responsivity of a photovoltaic cell, based on this photopillar diode, is also proportional to the height. That means we can enhance the conversion efficiency by playing on the height of the photodiode. And why the photodiode in this quadrant of the IV characteristic of the diode, it works as a sensor. But if we put it in this bias condition, we are in photovoltaic. Because why? At the end of the day, we are using the same photodiode more or less. Okay? Some crazy ideas we were thinking, and still I'm thinking, maybe in the future if we are lucky, is basically make an imager that on top of the layer, on the top of the imager, we harvest the light to power the ROIC underneath, that using the nanophoto pillars to acquire the image. So we can use the same structure, of course, more or less depends on the fabrications, okay? And we can basically have a batteryless CMOS image sensor. It's very, very interesting, and we call that concept sensor harvesting, because we are sensing and harvesting that like power. Of course, the applications are wide, especially for wireless endoscopic imaging, in which basically it is most stringent. I worked on this in McMaster basically, and it's the most stringent application for this kind of technologies. Why? Because you need really to consume as less as we can in power, and we need the highest resolution. So all the odds, they come here to make this pill, and it's still available in the market, but the technology development there is endless. And of course, the camera phone images, they are one of the hottest applications for this technology, as well as automotive, to name a few. Okay. All right. A team in Berkeley University, they worked on these pillars as well in different perspective, and they published also some of their findings there, but in a different way. But it shows one great aspect of the pillar photodiode. Basically, you can bend them basically and have a bending PV cell, which is really give the boost for wearable technologies. Okay. So again, with this technology that we suggest, we are trying to get the benefit of the front side elimination technology, which is a cheaper technology compared to backside elimination, by modifying the devices. So basically getting the cost of the front side elimination with the quality of the backside elimination. Okay, this is basically finished the first part of my talk regarding embedding intelligence. Now the second part is regarding the education, which is something that we should really give importance for our future generation. And for that, I suggest to embed intelligence in the education system. If you go to this talk, you will see what I'm talking about. So basically for this, I took the first definition of intelligence, which is the self-awareness. Education, to embed intelligence in the education system, or engineering education specifically, we need to make the self-awareness a very important component of the teaching. And that embed experiential learning, embed project-based learning, etc., etc. All of these techniques of teaching, they play the role of putting the student as a self-aware entity to make the intelligence to learn and to be self-driven. So the dynamics of education, as I said, is basically, it's not straightforward. It should be student-centered, student factored teaching methodology, and for that we have to encounter or include the psychology of the students. Okay, we have to bring different modalities in learning, and especially we have to make all of this around this self-awareness aspect, which really very important for the teaching of the students. I'll show you my experience in a second, but before then I have to tell you about the STEM engineering. The M is about that. STEM, science, technology, engineering, and math curriculum was started in a project by President Barack Obama back in 2009, and they poured billions and billions of dollars there, which is something fascinating. I just came from an American Society of Engineering Education conference where I published my findings there, and you cannot really imagine how much the industry and the academia are working on this STEM curriculum. And what is this STEM curriculum? Basically, to embed multiple disciplines, especially these disciplines, science, technology, engineering, and math, in the education system of the students. Okay, and I did that in the course I was teaching in fundamentals of microelectronics in the UAE, basically by embedding lab work in the class itself. Not to waste the class, but I do shoot the lab experiment, okay, and I bring it to the students. But before that, I have to prove to the students mathematically the thing that I want to prove with my experiment. So this is one of the applications of STEM that I endorse. So basically why we do that? Because one way only of learning is not enough. You have to approach the learning in different facets so that to convince the students of the importance of the thing they are learning. Okay? And why we do that? Why? Because artificial neural network, one of the aspects of artificial neural network or applications is called the content addressable memory or associative memory. And basically that the memorization that we use in our everyday life, basically we get different inputs and we associate them to remember them. Okay? That's in a nutshell. Okay? So one of the architectures I was working called bidirectional associative memory, it associates one layer of information to another layer through the synaptics, okay, that you can program them using any rule. I used at that time Hebbian rule, and how to implement this in the class. So basically, before the class starts, I have to embed the STEM in the presentation I'm going to give the students. And then these get recorded. Okay, of course I have to present in the class, and I record my class at the same time. Okay, and then when the students, after the class, revising, trying to understand or redigest what the student has learned, basically it associates the moment of learning with the video that the student is watching. By doing that, the aha phenomena or the déjà vu phenomena comes and enhances the learning process of the student. And that's where the associative memory basically. We associate the event with the picture or the video in this case, inside the brain of the students, and that's how we enhance the recall process of the student. So this is the neural network aspect or the artificial neural network aspect. I ran multiple evaluation pre and post exams, like for example this one, the pre-midterm exam of this methodology, we call it AIM, and after and also before the final, and just ask the students this question, how they like this blended learning in the sense of the class and also the video. Of course, they are all published on my YouTube channel, and most of them, more than the class, most of the class, they find it like very useful or useful. So almost 75% they agree with that, especially when comparing the final to the midterm. Why? Because the final, the amount of things they need to remember is huge, and any blended learning that can enhance their recall is much appreciated. And you can see this, the blue and the red, which basically the very useful and useful. Sorry about the resolution is not that great. They are higher than in the midterm. And then when I ask them also as well which resource they start to they use for revision, all of them they start with this. They use the PDF slides. Why they use the PDF slides? Because it's the highest depth of information. Okay? Because they can grab, they finish in very quick fashion. Now the second one was the textbook. Like if that's not enough, they go where? To the textbook. And it's the same profile, by the way. And if not enough, they go to the YouTube channel. Why? Because it's long and diluted to a great extent. Anyways, I published these findings, and I have other analytics on my YouTube channel. And here I quote some students, some nice quotes. So at the end of the course, they gave this. So, like for example, I want to read everything. I read the last one, which is the one I really like. Excellent teaching. The course was interesting, even if the class was at 8. Indeed, we start at 8 in the morning. It was fun with learning. The only class, we don't feel sleepy, which is really a great thing to read about this technique, that it has really helped the student that much. Again, to conclude, the biological intelligence systems, they are really available for us to learn and to embed in our engineering as well as education system, okay, to improve our education and the level of understanding for our students. The psychology of students is a very important aspect of learning. We should not take it as lightly, and we should factor it in this regard, and that the intelligence has different facets in life, especially for education. The self-awareness aspect, very important to let the student reflect on their understanding. Okay, and of course, by using various ways to learn, especially like for example STEM technique, we can enhance the understanding of the engineering and science courses as well, and blending different modalities, digital and in class, is another aspect that is really great for the education. Thank you so much for attending this rather lengthy seminar, and welcome all your questions. Thank you.
Okay, thank you very much. Do we have any questions?
Sure. So is this so I'm curious about the YouTube channel. Is this how you normally record
Yes,
class?
that's right. Yes, that's how I used to borrow a camera from university, but then I found that the mobile phone has a better camera, so I discovered I use mine then. It's much better and more efficient, yeah.
Why do you think they don't use that? The video.
The video.
If you looked at your statistics, your PowerPoint notes,
Yeah.
PDFs, was the most helpful.
Oh yeah. Yes, the slides are, yeah. Okay.
I don't have it.
Yeah, this one. Yeah. Revision again. You know, they are smart, the students. We are smart. If you want to revise and you want to finish the revision in very quick time, where do you go? You go to the most dense source. But then, when the student is stuck on learning one aspect, then they have to run. Where? To the more details, textbook. Then where? To the video as well. So again, it's just a matter of, you know, how much we can digest in how long. That's it. So they have to finish quickly. They start with the dance and go further. But definitely it helps. And it helps, why? Because the students, they reflect that. And there's an interaction component on that. They can even send me, they watch the video, and they basically scroll where they got stuck, and they basically leave me a comment below about it. And I receive that comment automatically by email, and they go there, I click on the time where they have put their comment, I click on it, I go there, and I read, I understand their question, and there I reply. And that reply will not be only for them, will also be shared by others as well. So it's a very interactive and very useful way of teaching, especially the student who gets stuck. Because that's better than saying, oh, I remember, sir, you said this and this and this and this. The professor maybe is too busy to remember. Maybe agree or not agree. But when there's a video, oh yes, I mean that, and the video is there, and it'll be shared by everybody, which makes this technique really quite interactive and very useful for students.
That's actually an interesting point, isn't it? You can go and identify the point in the class that is causing the confusion. So maybe what you need is some kind of, because you said the problem is the density of information, right? Is that that it's denser in the textbook than it is in the video. So maybe what you need is some kind of indexing.
Yes,
or
that's
something
true.
like that. That says a table of contents or something for the video.
Yes.
That enables the students to go to where they want to go to.
And yeah, that's actually, thanks for putting that. Actually, that's the next plan. The best, I mean, to finish this project is to go basically, I know the curriculum, I know what I passed, what are the elements, and the only thing I need to do, which in fact I did it in one of my talks, I go in the comment and put the time where each aspect we were talking. Okay, so, and the viewer can click on the time and automatically go to that aspect where we start talking about. And definitely that's very useful. It will be much better enhancement of the videos as they are right now. But that's the next step I'm planning to do, of course.
So I'm thinking of recording my lecture, but doing it a slightly different way. And that is during my PowerPoint presentation, I have a microphone.
Okay.
It gets recorded at the same time as the PowerPoint presentation, and you can output a movie of high-res version of your PowerPoint plus audio.
That's good. But
is that a Camtasia thing?
No, that's Keynote.
Oh yes, right, with
Built
recording.
into Keynote.
yeah, no, there are different
He's
techniques.
on a different.
Yeah.
But why I like this rather than this, I like the idea as well. But this one, I really want the moment of the learning. You know, students when they attend the class, they try to put their psyche and themselves in the mood of concentrating. I'm here to learn this. You know what I mean? And the visual, interaction between the teacher and the students make that bond of learning stronger. And when they watch that in video, it becomes like, hey man, I'm living that moment again. And that's the recalling process, which is another dimension, not only the content itself, but the human interaction between teacher and students. It really boosts the recall and the understanding process way further.
I move too much. I won't be in the camera.
I definitely.
So the issue here is that you both have two ways of, or you both consider two sources of information: the audio and the visual. But you have a different idea of what the visual is. Right? Your visual is the slides. Yours is you and the slides.
And the slides.
So
Yes.
what you want is three, in fact.
Yes. So the more you put
I
that,
will be creating the PDFs on my PowerPoint plus the video.
yes, you can.
And I'm wondering, do I do also the audio by itself so people on the bus can listen? I don't know.
Yeah, sort of podcast.
Yeah.
But the generation that we have here, students, they are on the go. I mean, we need to give them the courses at their hands. They are bonded by mobile. In fact, I got this idea starting from Kuwait. I was teaching physics by then, and as soon as I give them break, as soon as I say break, they start mobile. They are so bounded by the mobiles that they became problem for me. Sometimes even asking students not to use their mobiles in class. So I said, why fighting the mobile? Give them the mobile. That's it. You see. So really, this will help the students further, in their learning, especially with the amount of information they have. It's good to give the course to them on the go. That would be a
I prefer YouTube to, let's say, mounted locally.
Really, I don't have really preference there, but locally is good. It depends what's your target, really.
Right.
For me, I wanted really to show my technique of teaching everybody.
And what your local support is.
Exactly, yeah.
This YouTube is.
The reason I ask is there's some copyright issues, and to what extent do you want to? Are you giving up copyright when you put it on YouTube?
Yeah. It's common knowledge. It's a common thing. I think the slides are mine actually. It's up to 95%. They are mine. I do them myself. So it's me giving others to use. I agree. There's copyright issue between private and make it public, definitely. But in terms of teaching technique, it doesn't matter really. As long as the students have access to that, it's okay. And of course the support. YouTube have lots of support in terms of image processing, comments and things like that. I don't know if it's local, then why not?
So I was going to just simply put it on our 1 terabyte Office 365.
Yeah, why not?
Point students to it.
Yeah. And I do like this business that the students can time index the bit that's confusing.
Yeah.
Actually, and be able to rewind it, because that's quite powerful. Because
Yeah.
quite often I find on exams or whatever, quite a bunch of number of students regurgitate the same wrong thing, which is often well, there's a number of possibilities, but one is that something you said was confusing.
Yes.
And it's useful to be able to get back to that.
Yeah, definitely.
What it is, which I hadn't actually thought of before. So it's good. Thank you.
The moment, thank you. Yeah, the moment, the learning moment is very important.
It's also great for TFP.
Yeah, that's what it is. So the question is, can you so going back to what do you present in the movie?
Yeah.
It'd be quite interesting to see how far you could, by eliminating various things, where do you get to the point where it's useful? So all of the different elements you can record or present, and the ways you can present it, which are the most effective? I guess can you cut out the picture of you talking, like John has suggested?
Yeah.
And compare the results, because it might be, you're right, that in fact seeing you gesticulating is a helpful part of the process. I see research for it.
Yeah, definitely. Yeah. No, it's really to have evaluation on these techniques. It has to be clinically done, because it's you have to, especially when it comes to quantization of the learning aspect. It's very hard to do it like in every day. But if you do it clinically and you try it, that's how it should be really evaluated, to be specifically. But really, from my general understanding and interaction, I think the teacher is a major component in the learning process. Because just watching the slides or hearing is just an addition. It's very good, but also the gestures, the interaction. That's very as much as you add to that moment of learning, you get that to the students. Is good. Sound, video, you name it, whatever you can.
And you give them PowerPoint beforehand?
I give the slides beforehand. Yes. Yeah, definitely. Because at least to prepare them. Really, the idea is actually to make this further is to do the flipped classroom.
Yeah.
I could not do it at that time for many reasons, but the idea is to give this to students and in the class solve problems.
Just curious who makes this.
I bought this from a different company, Walmart, and this one I bought it from where? I don't know. Okay. But they were bought separately.
And you need a power brick.
Yeah.
So the other way that some of our colleagues are doing this is addressing the issue of density, is to do these very short videos.
Yes.
And so James, for example,
that's right.
He identifies a particular skill or technique or approach or recipe or something.
Yes.
And he does a 5-minute video that says, if you want to do this, watch this video.
Yes, absolutely.
And that seems to be really good.
Yeah, definitely. Yeah.
It's not so much the main part of the course, but elements of things that people need to do. Particularly, I guess, in certain operating system environments or something like that. To do this,
Yeah, this is very similar to Khan Academy, for example. Khan Academy. It's very similar to that. So basically, and I'm using that to teach my kids, all of them, from grade 2 up to grade 8. So the Khan Academy is specifically you can click on specific aspect, watch it, and then do the solution and tackle the problems. It's very, very, very nice. Although his picture is not there, but his voice there and the board is there. But it does boost. Really, all my kids they love it and they enjoy it.
Because in a sense, the lecture is just a sequence of these parts.
Yeah.
So for me, it's like that, huh? Any of the AirPods?
Yeah.
I could be anywhere in the room.
Well, that's good.
That technology
transfers it through.
It transfers it to the laptop.
Have you talked to Jit about this? Because Jit's trying to do the same thing with his version of the new iOS 11.
Okay.
And so he's having some problems because it's not doing all the parts he wants it to do. But he's trying to use this thing to record it.
Okay.
So have a chat with Jit.
But I like this idea too.
Yeah. No, it's interesting. So that's just a power.
Yeah.
That's just for power.
Yeah. Yeah, it's a nice little stand, isn't it?
Yeah, I was looking really at. I had a tripod before, and it broke after because. But this one does not have the mechanic. It has the rotation thing, so that's why I got it. Yeah, and this is basically selfie stick. This one, this is selfie stick. Nothing more, really.